When stress hits a global mobility network, the impact rarely stays isolated. A slowdown at a single port can violently cascade, pulling down connected systems hundreds of miles away. For U.S. Transcom, the global mobility mission relies on exactly this kind of architecture: tightly coupled, interdependent networks, where ports, transportation corridors, fuel allocations, and timing constraints operate as a single unified system. It is common to treat disruptions as component reliability problems, assuming a network fails simply because a localized piece of hardware or a single routing node breaks down. But complex networks operate differently. Catastrophic collapse is a phase transition. The system actually degrades when cross-domain dependencies synchronize under intense stress. Treating this dynamic, interdependent system as a series of isolated components guarantees operational failure when large-scale stress finally hits the architecture. The current industry standard for managing these networks relies heavily on monitoring dashboards. These tools are designed to answer one specific question: where is the disruption visible right now? Answering that question means the observer is already too late. If you are looking at a red light on a map, the failure cascade has already started. By the time a slowdown becomes observable at the joint operations level, the opportunity to execute a preventative intervention has completely closed. This brings us to a mathematical dividing line known as the percolation threshold. This is the exact point separating a network that can hold its shape from one locked into an irreversible collapse. Look at how a network behaves just before it crosses that marker. The impending collapse is structurally guaranteed by the math, but to a standard monitoring dashboard, the system still looks perfectly stable. Relying on real-time dashboards locks you into a reactive posture. True command advantage requires identifying when the network is converging toward instability long before you have to observe the aftermath. It is easy to assume that cascading network failures are sudden, unpredictable strikes of bad luck that simply cannot be foreseen. The science of temporal percolation theory proves otherwise. There is a specific, mathematically defined period right before a collapse, known as the pre-threshold window. This diagram illustrates a network moving from a subcritical, stable state to a supercritical, failing state. We can mathematically isolate the transition phase in this highlighted mathematical zone, the pre-threshold window. Capturing this mathematical window provides a concrete 24 to 48-hour operational lead time before throughput physically degrades on the ground. This temporal math forms the foundation for AIM-PTC. It is a new class of anticipatory infrastructure intelligence explicitly designed to capture this specific window. Operating inside that window means you are actively stabilizing the network. Missing it means you are paying for a reactive, costly recovery. AIM-PTC is built as an embedded intelligence layer. It sits directly inside existing U.S. Transcom systems, avoiding the need for a disruptive platform replacement. Looking at this architectural diagram, the blue layers show how the system continuously ingests disparate data streams across logistics, transportation, and distribution channels, completely invisible to current workflows. Those inputs feed directly into the core processing engine, the dynamic multi-layer dependency graph. This graph formally maps the hidden interdependencies between ports, routes, fuel, and strict timing constraints. From there, the AI intelligence core applies temporal machine learning and actuarial risk methods, constantly calculating how close the network is to collapse. The architecture takes raw, isolated data streams and translates them into a unified, predictive map of systemic risk with exact cascade probabilities. To see how this architecture performs in the field, we can trace a concrete operational scenario. On the right side of this chart, an initiating event occurs, an environmental flood causing localized reservoir stress. Standard systems track this in isolation, but utilizing explainable AI, the system maps how this connects to broader logistical consequences. Tracing the XAI pathway, the reservoir stress forces a water release, threatening to flood downstream power substations. Ultimately, this substation pressure triggers a severe disruption across the connected transportation network. The system generates actionable output, a high cascade risk score of 0.78 and a time to impact of 56 hours, opening the intervention window. The system detects upstream environmental convergence days before downstream logistics operators ever see a physical delay on their routes. This raises a critical operational question: What exactly does a joint mobility decision maker do with a 56-hour warning? The answer is the pre-threshold execution layer, or PTEL. It is the operational mechanism designed specifically for intervening before throughput collapses. PTEL allows pre-positioning routing adjustments, allocating critical fuel, and staging distribution resources directly against predicted systemic risk. This anticipatory maneuver stands in sharp contrast to the costly method of waiting to react only after physical delays have already rippled across the theater. This dashboard highlights concrete operational metrics delivered to U.S. Transcom, starting with a 24 to 48-hour actionable lead time. Executing decisions within that window achieves the second target, an estimated 15 to 25% reduction in total network disruption. The pre-threshold execution layer takes predictive intelligence and immediately transforms it into preemptive operational maneuvering, securing the logistics chain before it breaks. The immediate deployment strategy integrates the system via a shadow mode pilot, running continuously within a high-complexity U.S. Transcom operational environment. Deployment governance is rigorous. The transition to a live operational advisory capability is strictly gated on demonstrated validity, never on arbitrary schedules. As it runs, the system's regenerative layer continuously updates its understanding of network interdependencies based on observed real-world operational outcomes. The ultimate objective is shifting global mobility operations permanently away from reactive execution, moving instead toward anticipatory network stabilization. In contested logistics environments, command decision advantage belongs exclusively to those who can control the pre-threshold window.